Hello everybody, my name is Ramos.
My name is James Ashe.
And I'm David Lara.
And today we'll be presenting the Nautical Emergency Desalination Device, or NEDD for short. Our goal for this project was to create a portable water desalinator that could be used in an emergency situation. This device will provide enough water for individuals or small groups to remain alive as they await rescue. In addition, it would also be more affordable than current products in the market. Project motivation. In a survival situation, one of the most important aspects is, or one of the most important resources is clean drinkable water. However, over 70% of the Earth's surface is covered with undrinkable salt ocean water. This is why the NEDD will increase the chances of survival for someone in an emergency situation significantly. A little bit of background on the subject. Desalination is the process of removing salt and minerals from a target substance. One of the ways to do this is through reverse osmosis, which is the process of applying high pressure to a solvent, in this case water, and push it through a porous membrane in the direction opposite to natural osmosis. This separates the permeate, which is the clean drinkable water, from the concentrate, which is the excess salt water. In addition, the daily water intake for an adult is between 2.3 and 3.3 liters of water a day. And existing similar products, such as the Catadiene 06 Survivor, cost over $1,000. Here are some of our design alternatives. The first is a mechanical hand pump, which consists of a piston lever system that would push the water through the membrane. Our second design is a hybrid pump, which would consist of a rotary electric water pump that could also be operated manually. Our last design is an electric pump, which is just a water pump that is powered by either a solar panel or a wind turbine. Additional value. Apart from providing clean drinkable water, we also want to increase the chances of rescue. Therefore, we are going to add a rescue light, a radio, or a phone charger to our system in order to increase this chance of rescue. It is important to note that these electronics would be separate from the water production unit. So in case that it is damaged due to water damage or something like that, it does not affect the water production. In addition, there are no current products that bring together rescue aids and water generation right now. Within the mechanical design alternative, which is what we are considering right now because it is more practical for an emergency situation, we have two alternate designs as well. The first is a regular design which intakes water from the ocean and forces it through a piston to the RO membrane. The second design is a recirculation, which recirculates the concentrate back into the intake tube, and what this allows for is for already pressurized water to come back into the system, which would then reduce the amount of work that the user has to exert on the system. Like I said, so far we are going with a mechanical design, and this is our prototype so far. Of course, it includes a lever piston pump, as I mentioned before, and a small tube that routes it to the reverse osmosis membrane.
So when we're starting our modeling and design, we need to look at things from a technical standpoint. So the best way to start is by looking at our membrane, which give us these following dimensions, which allow us to look at what size of tubing we need, so on and so forth. Furthermore, we have a glimpse of our recovery rate. So for example, this very membrane has an 8% recovery rate, meaning that, for example, if every 100 liters go into the system, only 8 liters will actually become drinkable water. So to sort of scale what we need to see, we're using Bernoulli's equation. We're assuming an adiabatic and isothermal system, meaning no heat is coming in or out. And we're looking at major factors such as how much power does the pump need to generate the output that we want? What is the necessary flow rate? And what are the potential losses? So when we're looking at our factors, we need to sort of look at every factor and see which ones matter to us in our design or not. So we're looking at negligible factors. So what we're looking at is an input flow rate of about 0 to 100 liters per hour. Now, considering massive losses, in other words, if our pipe was about the length of a football field and made of wood. So very extreme, circumstances that are exaggerated, we can see that it won't do much more than a watt of power difference. So we can say that those losses are not very significant. So when we're coming up with something such as a pipe or a bladder system, we can worry more about sort of the ethics and the cost-benefit analysis behind it. And another thing we're sort of looking at is the depth of the tubing. So if we were to have it about 100 inches down or about 10 inches below sea level, you can see right here that it won't make a difference at any flow rate. And so the system that we're using, we're considering two different tubes of two different diameters, which we define as sort of a ratio. So when we look at the different ratios, we can see that at the very end, around 200 to 250 liters per hour, there is a significant difference. However, at the range we're looking at, it is not. So what we have here is basically design freedom from a technical aspect, meaning we can look at sort of, for example, we can look at a material that's cheap, but we can't sacrifice the ethics behind it. For example, we're not going to use lead in our system because while it may be cheap, it may contaminate our water. And really, when we look at the average power that we need, for example, we're looking at about 1 to 5 liters per hour of drinkable water. So if we assume 8% recovery rate and we put in, say, 50 watts of power, we get about 2.64 liters an hour of drinkable water.
With regards to the standards that we'll be compliant with in our design, one of the key organizations that we'll be looking at is the International Maritime Organization, which is the branch of the UN. They've outlined very specific standards for performance and testing, specifically for manually operated desalinators that work using reverse osmosis. Their standards include things like the amount of force, the maximum amount of force required for a person to use in order to operate the device, as well as other things in terms of material usage and operating temperatures as well. We'll also be looking at the U.S. Food and Drug Administration as well as the Environmental Protection Agency. Both of those organizations outline standards for drinkable water, and the EPA also outlines standards and codes regarding disinfectants that will be used to clean the system, as well as sustainability in order to ensure that the device does not harm the environment, since one of the settings that we'll be looking at for this device to be used on is open water in these conditions. At the component level, we'll be largely looking at the American Society of Mechanical Engineers regarding their standards on pressure vessels, the pump mechanism, as well as other mechanical components as far as like fittings and screws and things like that. With regards to hybrid and electrical designs, we'll be looking at the IEEE, the Institute of Electrical and Electronics Engineers, for things such as solar panels or the wind turbine, as well as looking at standards regarding waterproofing. For our global design considerations, any listing of units will be both in SI and Imperial units. Our user's manual will be multilingual in English, Spanish, French, as well as Japanese, and will include a visual handbook that will have universally recognizable symbols to instruct the user in the operation of the device. We're looking to have little to no electrical components, if possible, so as to increase the practicality of our design for emergency use and to increase its reliability. The design itself will be simple, durable, and mobile. Going forward, we'll be doing simulations as force and stress analyses for the electric pump as well as the mechanical pump designs. We'll be making sure that to do a failure analysis to ensure that under the high pressures required, our device will not fail. As well as a cost analysis for materials as well as components that we'll be purchasing in order to construct our prototype for the pump, the reverse osmosis membrane, and any tubing required. Here we have our Gantt chart, which outlines our timeline for our project. Starting earlier this year, it was just formulating and coming up with what exactly would be our project. Moving forward, We did research into how it would work, as well as coming up with the design itself. Right now, we're in the phase of coming up with our design concept. As you saw, a few engineering drawings on our mechanical pump design. Moving forward into the summer, we'll be working on collecting the parts and components required and actually constructing the prototype. Moving into the fall, we will move into testing and coming up with a final design going into the winter. And throughout the entire process, we'll be working on updating our thesis.
That's our presentation. Thank you.
Thank you very much. Any questions?
My 112-foot yacht just sank, and there's 9 of us in an 8-person life raft in 6-foot seas. You got to think about that when you're designing this, because that's a more likely process than somebody that's in a life raft with lots of room, or somebody that goes up on the beach on an island somewhere. So you really need to think of a place that's going to be very, very isolated if that's the device that you want me to buy to save my life.
Right. Well, we're thinking of adding a flotation device so that, for example, if you're in an unfortunate situation where you're not in a life raft or you're not by the coast, you can at least rely on our system to stay afloat, at least to do its job. Furthermore, that's sort of why we are leaning more toward the hand pump, because when we're talking about adding an electrical system, that sort of falls into the risk if, for example, in your situation, in which case the electrical system may be exposed to salt water. And as designed, that would most likely mean we would have to do a lot more sealing, which may increase the price of our total design.
The other thing that happens is people take something like this and they don't think they're ever going to use it, and they put it down below in some drawer, and they let it sit there for years and years and years with never being operated. It shouldn't be that way, but I think practically you've got to have something that the seals aren't going to corrode or rot. So you have to think about all of that when you're doing that.
I agree. Many of those things are covered under the IMO standards in terms of their endurance testing.
Right. For good reason.
Yes.
Okay, and again, the comment of survival was really important to me. And I do agree with the comment of buoyancy. You need to make sure that this thing is capable of floating on its own, and that you don't have to do anything special to make it float on its own.
Right.
You need to make sure that you've got some kind of a capture device designed into it, so that when it goes over the side, I have the ability to get it back. You need to have hoses on it of sufficient length that I don't have to hang over the side of my ship in order to get to water, because of worry of me going overside. The weight of this needs to be designed into it so that it's something somebody can easily use. So I mean, there's some of your design criteria that needs to be user-friendly. Making the assumption exactly as he communicated, I might have a ship on its side that I have to work from. I may not be working from a flat platform. Packaging issues and things that you should think about is shock testing or drop testing. Well, if somebody dropped this thing, would it break? Because things will happen while you're on the ship. Fouling. One area that I would think you need to be careful with is that if I'm out there an extended amount of time that I put too much salt in that filter, do I have a way of backwashing that system to be able to get myself back to a state where I actually can get desalination system? By fouling, is the system designed so that I don't pick up, dirt and stuff and clog up that filter quickly? Again, your international standards, I'd love to see how you're going to be compliant to them. Okay, so saying that you do it, show us on a chart that this is what the requirements are and this is what you did to meet those. And then the last statement I want to make is on flow simulation. I'd love to see a flow simulation model and testing and show us that you either meet or you don't meet, the reason why. Okay. That's a lot,
But it's necessary.
No, it's
Okay.
necessary, it's completely necessary.
okay, thank
So
you.
I have a couple of comments as far as your validation as well. I would like to see that you test the salinity level on the water after your pump is done, as well as just the standard pH levels, making sure that your materials are not contaminating, or the materials that you choose are not contaminating the water that you're filtering. Also look into your filter. You don't just want to filter the big objects. You want to filter those stuff you cannot see. If there's any bacteria in the water or anything that will end up making you sicker than you are, that'll inhibit dehydration. I would stay away from metals. You're putting this in salt water, so that's something else to consider. And also look into your salt levels. There is a percent of salt or sodium that you can have in water that actually helps you, electrolytes. So don't try to target 100% removal. See what is healthy and try and target that.
Well, the filter that we were looking at previously actually has a removal rate of about 99.2%. It's not a removal of all the salts. So we will have some salts that will be, beneficial. As far as, say, for like the filter, we have been looking at a sort of a filter before it goes into the system that makes sure there isn't like any larger grains or any potential marine wildlife that may contaminate the water. And you're absolutely right about the idea of material. Some major downfalls of using metal is, one, under salt water is extremely corrosive, and some cheaper metals such as lead is extremely dangerous because it is a contaminant. For sure, one of our major factors has to be the weight of the system. When we're talking about buoyancy, the weight of the system does play a huge role.
It's not just buoyancy, right? If this thing weighs 100 pounds and you have to operate a 100-pound filter, when you're, again, going to this example, 8 people on a life raft, now it becomes more of an inconvenience than a survival. Yes, sir.
And if it sinks, it goes overboard and it's gone.
Yeah.
Plus, it's got to float full because the water's going to weigh it down once you start using it. So you take that into account as well.
We don't want this to be anchor for the most part. All right, any other questions?
It will.
Last thing about wind power, I would consider looking at what's reliable in the ocean. You can have days that are extremely windy, but you can have days where there's absolutely no wind. So you're leaving it, to Mother Nature to dictate whether you have drinkable or not drinkable water. So solar power, the hand pump, those are things that you at least know you might have better luck than with wind. So just keep that into consideration.
Yeah, guys, I would think you'd want to go manual and almost make that requirement initial, because there's a ton of other stuff you need to do. Because if any of the other applications, you sit these in his boat for 7 years, you're not going to work the day you need it. Whereas manual, at least you have half a chance of that. But the key statement is that put your time into the packaging and the shock testing and design, the mechanical design of the function, and less time into the thought of an electromechanical, which would be a tough play in that environment. That's a suggestion.
All right, thank you very much.